today I'll be simulating a natural convection in a square cavity using Ansys fluent. So let's start with that. First of all, we'll drag fluid flow fluent over here and open a new design modular geometry. Then we'll make a square cavity with that. Then give us opening. Just wait. Okay. XY plane. Start sketching. We'll just zoom in a bit. Then go to sketching and then rectangle. Draw a random rectangle. We'll just give the dimensions. This and this. We'll be making a square cavity of 1 meter. Edges and this and good for square. Then we should make it surface from sketches. We'll select all the 4 lines, apply and generate. So this is our square cavity. You can also name it, let's say, fluid. Okay, generate. Okay, that's all done. We're all done with design modeler. Then we'll open mesh. We'll start meshing. We'll do some meshing and then go to setup, update it. Okay, so here's our diagram. Let's see. This is x-axis, this is y-axis, and let's mesh it and let's put in the elements as 0.01 meter and then generate mesh. Okay, as you can see, our mesh has been generated. It looks fine to me. So now we'll just put the name selection. Edge, select edge. This will be the top valve. This will be the left valve. Left valve. This will be the right valve. Right valve. And the bottom one will be bottom one. Bottom valve. Okay, so all of our name selections are here. This is full fluid, top valve, left valve, top valve, left valve, right valve, bottom valve, and this is our mesh. We're done with the meshing. Now let's start to solve it. We'll update it here. The name selection was not updated. Now I'll open setup. Since it's 2D, so it's locked in 2D options. We'll use double precision and start. Starting fluent. It might take some time to load. Okay. So first of all, it should be pressure based, absolute, steady and planar. We'll add gravity along negative y direction, so we'll just put -9.81 vertical negative y direction. We'll put gravity models, we'll activate the energy equation, and then we need a laminar flow, so we'll just select viscous here and select laminar. Okay. Radiation heat exchanger species, we don't need that right now for our problem. Materials, fluid, solid, fluid, air. Material is air, type fluid, density. We'll take Bosniak density, and here we'll put the value 1.1405. With the thermal expansion coefficient, which is 0.00. 2033. Okay, change the grade and please. Material is done. Present conditions, fluid, obviously. Let's see. Yes, everything is alright. So let's go with the boundary conditions. The valve. So start with the left valve. Left and right valve are supposed to be isothermal. So left valve, the stationary valve, no slip. Okay. Temperature. We need to put a temperature difference. So on the valve is left valve. Left valve will put 310 Kelvin. 10 Kelvin applied. Close and right valve. Let's go with this obviously stationary valve, no slip. With flux and temperature. Let's go with 290 Kelvin. Okay. Apply and close. Left valve, right valve. Let's move top valve. Our top valve is adiabatic, so there will no heat flux. Maybe the temperature is right. Close. Now for bottom valve, we need to define something. We will go to named expression. New expression. And define a value L. L is the length, and I'll put it 1 meter. 1 and unit is meter. Okay. Okay. So you can see L, definition 1 meter, dimension is meter. Okay, close. Now we can write the bottom valve equation. The bottom valve will have a heat flux, which equation was given to us. It will be Q naught sin pi x by L. I'll just enter the equation here. First of all, we will have expression. This is multiplied by sine of pi into x divided by L. Let's go see. It's okay. We will plot. We can also do the plot if we just maximum value. Suppose 1000. It just says that it's a sinusoidal wave. Obviously, this is okay. We will just apply it. 1000 sine. I have taken Q naught to be 1000. 1000 sine pi x divided by L. We have applied it. I'll close. Okay, so we have done this. Now we'll go to methods. Pressure velocity coupling scheme, we'll do simple, and the written rest we'll just keep it as it is. Now we've done this, so we'll just go for initialization. We'll hybrid initialization, it should be initialize it, hybrid initialization is done. Hybrid initialization is done. Calculations, number of iterations, let's say 1000 iterations, and 1000 like this. Okay, now I need monitors, residuals. This is correct values, 10 to the power minus 6 and Z, as well velocity 0.001, 0.001, and the same is for continuity. We are done here. Calculate. Should see a graph. We go to 1000 iterations. Should converge to 10 to the power minus 6. Continuity should converge to 10 to the power minus 6, and these three should converge to 10 to the power minus 3. It will go down. calculation is complete. So let's see our results. What is this? Results. So open graphics, contours. We do the contours of temperature and velocity. Contours of temperature. Okay. Save and display. Control on static lines. This is what we got. So temperature is maximum. No one knows. Okay. Let's now take contours of velocity. Save display. This is the velocity contour. Here it is, velocity contour, and we have solved the problem.